So good morning to one and all. Your course name System Design and Control. In that we are going to discuss about the frequency response analysis. First of all, what is the frequency response? So frequency response is the steady state response of a system when the input to the system is a sinusoidal in nature. So what are the merits? So the absolute and relative stability of the closed loop system can be estimated from the knowledge of their open loop frequency response. The second point is the practical testing of the system can be easily carried out with the available sinusoidal signal generator and previous measurements of the equipment. Your third merit is the transfer functions of this complicated system can be determined experimentally by frequency response test. The design and parameter adjustment of the loop transfer function of a system for a specific closed loop performance is carried out easily frequency domain. Your fifth merit is the frequency response analysis and the design can be extended to certain non-linear control system. So the definitions, that is the response of a system for the sinusoidal input is sinusoidal response. The ratio of sinusoidal response and sinusoidal input is called sinusoidal transfer function of the system, and usually it is denoted as T of j omega. The sinusoidal transfer function is the frequency domain representation of the system, so it is also called frequency domain transfer function. So here the sinusoidal transfer function can be obtained as shown below. First, you have to construct a physical model of a system using basic elements or parameters. Then next, you have to determine the differential equation governing the mechanical systems for a general system from the physical model of the system. Next, we have to take Laplace transform of differential equations in order to convert them to a S-domain equation. Next, you have to determine S-domain transfer function, that is T of S, which is a ratio of S-domain of output to input. Next, you have to determine the frequency domain transfer function T of j omega by replacing S by j omega in S-domain transfer functions. So in simple, we can convert a T of S that is equal to T of j omega. So next, frequency domain transfer function is a complex function of omega. Hence, can be separated into a magnitude function and phase function. Now, the magnitude and phase function will be real functions of omega. They are called as frequency response. Here, the open loop transfer function g of s that is equal to, in frequency domain, we have to replace here s with j of omega, therefore g of j omega. That is nothing but here modulus of g of j omega, then angle of g of j omega. Whereas your loop transfer function, that is g of s into h of s, that is equal to g of j omega into h of j omega is equal to modulus of g of j omega into h of j omega with the angle of g of j omega h of j omega. Likewise, your closed loop transfer function, that is m of s, that is equal to s of j omega and again m of j omega. For that, we have a magnitude function. In simple, for a frequency domain, we have a magnitude function as well as here frequency function, that is a phase function also. Next, what are the different frequency domain specifications? So the frequency domain specifications are, first one is a resonant peak. Your standard notation is the m of r, and a resonant frequency omega of r, bandwidth omega of b. Next one, cutoff rate, then phase margin k of g, then gain margin k of g, phase margin gamma. So the resonant peak, the maximum value of the magnitude of closed loop transfer function is called the resonant peak, that is m of r. A large resonant peak resembles to a large overshoot and transient response. Frequency, resonant frequency, the frequency at which the resonant peak occurs is called as a resonant frequency, that is omega of r. Next, bandwidth. The bandwidth is the range of frequencies for which a normalized gain of the system is more than minus 3 decibel. The frequency at which the gain is minus 3 dB is called as a cutoff frequency. Next, a cutoff rate. The slope of the longitude magnitude curve near the cutoff frequency is called cutoff rate. The cutoff rate indicates the ability of the system to distinguish the signal from noise. Next, resonant peak. The maximum value of the magnitude of closed loop transfer function is called resonant peak. A large resonant peak results to large resonance. So next, you have to move on to gain margin. So gain margin is defined as the value of gain to be added to a system in order to bring the system to verge of instability. So the general equation, that is a gain margin, that is equal to Kg. So the notation is Kg, that is equal to 1 divided by modulus of G of j omega Pc. So the gain margin in dB can be expressed as Kg, that is nothing but your gain margin in decibel, that is equal to 20 log of Kg, that is gain margin. Again, that is equal to 20 log of 1 divided by G of j omega Pc. So where G of j omega Pc, that is the magnitude of G of j omega at here omega, that is equal to omega Pc. Therefore, in simple, the gain margin in decibel is given by the negative magnitude of the G of j omega at phase crossover frequency. So the gain margin indicates the additional gain that can be provided to a system without affecting the stability of the system. So next we move on to phase margin. Phase margin is defined as the additional phase lag that to be added to gain crossover frequency in order to bring the system to edge of instability. So the gain margin gamma is obtained by adding 180 degree to the phase angle of phi of the open loop transfer function at a gain crossover frequency. So for the phase margin, that is equal to gamma, that is equal to 180 degree plus pi gc, whereas pi gc, that is equal to angle of G of j omega Pc. So angle G of j omega Pc is the phase angle of G of j omega at omega is equal to omega gc. The phase margin indicates the additional phase lag that can be provided to the system without affecting stability. So what are the different response plots? We have different graphical techniques for the frequency response analysis. Here, first one is a Bode plot and a polar plot, other is called as a Nyquist plot, and the third one is Nichols plot and the M&N circles and Nichols chart. Whereas the Bode plot, polar plot, and Nichols chart are usually drawn for an open loop system, and from that open loop system, the performance from the open loop response plot, can able to predict the performance and stability of the closed loop system. So the M and N circles and Nichols chart are used to graphically determine the frequency response of the unity feedback of a closed loop system. So that's all about your different plots that can be used for a frequency response analysis. Here from the frequency response plot, we can able to determine the frequency domain specifications to study the stability of the system and to adjust the gain of the system to satisfy the desired specifications. So from this part, we can able to find the stability of the system. So thank you one and all for watching this.